In lesson 12.1, we're going to look at some basic definitions of complex numbers. When we've been in our study talking about real numbers, and because when you take a number and square it, whether it's positive or negative, you always get a positive answer, right? So we could take the square root of something like a positive 25, but we couldn't take the square root of a negative 25 because there was no number times itself that would give us a negative 25. So what we've got now that we need to consider to help us with that is a complex number system. So in our complex number system, we have a complex number that can be written in this form. And I'd like for you to notice, first of all, this up here at the top in the shaded box right here. This is our key right here. And in previous math courses, it was probably called I, but that's an imaginary number that's equal to the square root of negative 1. So instead of saying square root of negative 1 equals 1, it doesn't. The square root of negative 1 equals I. So when I square both sides of that equation, we end up with this fact, that I squared is equal to negative 1. Now, that's in traditional math classes where we use the letter I. But in this course, we're going to be using the letter J to represent this imaginary number. And the reason behind that is one of the major technical applications of complex numbers is in electronics, where I represents electric current. So therefore, we will be using J for the square root of negative 1. Now, I may goof up and say I sometimes, but I'm going to try to stick with the J here. Okay, so a complex number is written in this form. It's written as A plus BJ. Okay, so you have two parts to a complex number. You have the A, which is the real part, and then the BJ, which is the imaginary part. And in some cases, if you have a number that only has BJ, that's called a pure imaginary number. If the value of B is 0, then the BJ drops out and we have just A, and A is the real number. Okay, so A plus BI, or BJ, is known as a rectangular form of a complex number, where A is the real part and B is the imaginary part. Now, one of the things I'd like for you to notice here is that when we consider J raised to the 0 power, we know that any base raised to the 0 power equals 1, right? And then we've got J to the first power, and we know any base raised to the 1 power is equal to itself, which is J. And then by our definition up here at the top of the page, we have J squared, which equals negative 1. Now we don't have J to the third. So what we're going to do is we're going to think of that as being J times J squared. And when we do this, the J squared equals negative 1. So we're really looking at J times negative 1. So J to the third power is equal to negative J. Okay, I hope that makes sense. And then when we come back around here and we have J to the fourth power, J to the fourth power is the same thing as saying J squared times J squared, right? And we know that J squared is equal to negative 1. So we've got negative 1 times negative 1, which equals 1. Okay, we don't want to have to go through that every single time. So what we're going to do is we're going to use these first three facts and then consider the remainders when we divide these exponents by 4. So for example, if I had something like J raised to, we'll say, the 15th power, and I want to simplify that. When I divide 15 by 4, that's going to give me 3 with a remainder of 3. So all I'm focusing on is the remainder. So j to the 15th is the same thing as j to the 3rd, because that's the remainder. And I know over here, j to the 3rd is equal to negative j. Okay, so that's how we're going to simplify some of these complex numbers, or imaginary parts of the complex number. Now I have 3 problems here I'd like for us to consider. And the first one says to express that complex number in terms of j. So that means they want us to use the fact that the square root of negative 1 is equal to j. So taking care of that negative sign is no problem. We're just going to bring a j on the outside. Square root of 18, we're going to think of that as, I'm just going to put j on the outside here for that square root of negative 1. 18 is the same thing as 9 times 2. So I've got 2j, my handwriting is terrible tonight, 2j times the square root of 9 times 2. And the square root of 9 I know is 3, so I'm going to bring that 3 outside of the radical and multiply it times this 2j. So my final answer is 6j times the square root of 2. That's how we'd simplify this 2 square root of negative 18. Now, in this one over here, we're thinking about those powers, right? When I have a negative outside of a base raised to a power, that just means you take whatever your final answer is and you put a negative in front of it, or take the opposite of it, in other words. So here, the remainder, when we divide 14 by 4, is 2. So this is the same thing as saying negative j squared. And I know that j squared is equal to negative 1. So this is the same thing as negative of negative 1, which is equal to 1. Now, when the negative is inside the parentheses, raised to that power, that means I've got to raise the negative to the power as well as the base, j. So I'm really thinking of this as being like negative 1 raised to the 14th times j raised to the 14th. Kind of separating it here a little bit. So negative 1 to the 14th, well, any negative raised to an even power like that's going to be positive. So all of this right here just becomes a positive 1. And then j to the 14th, I'm thinking, okay, what is the remainder when I divide 14 by 4? That's going to be 2. So that's equal to j squared. And I know that j squared is equal to negative 1. So I've got to be careful. It does make a difference if the negative is inside the parentheses or not. Now with the second one here, I want to find the values of x and y. Those are my unknown variables. So in the problem, I want to look at it as a real part and an imaginary part. So here the real part would be x plus y, or I'm sorry, x minus y, excuse me. That's the real part of the left-hand side, and the imaginary part is the 2j. So I'm just writing it, I'm trying to make it look like a plus 2j, or a plus bj, excuse me. And then on the right-hand side, there is no real part, because both of these have a j. So it's kind of like an understood 0 plus, and I'm going to factor out the j, so that leaves me with y minus 3x. And that's times the j. So in this problem here, the real parts would be this x minus y, and 0. Those are real. And the imaginary parts, let's see if I can get a different color up here. Imaginary parts are this 2 and y minus 3x. So I'm going to use two equations and solve that system of two equations and two unknowns. So setting the real parts equal to each other, I've got x minus y equals 0. And setting the imaginary parts equal to each other, that's going to be 2. See if I can write this down. 2 equals y minus 3x. So I've set the real parts equal, the imaginary parts equal. Now I've got everything in terms of x and y, and the question was to find those values of x and y. So we've got, we've learned several methods to solve a system of two equations and two unknowns. Everything from graphing to substitution to addition, subtraction to matrices. So you could use any of those techniques. When I look at this, though, I'm looking at x minus y equals 0. I'm thinking, oh, that's real easy to solve in substitution, because if I just add y to both sides, I now know x and y are equal. That means x is equal to y. And then I can go back in the other equation and make a substitution. I can replace this x here with y, and now I've got 2 is equal to y minus 3y. And y minus 3y is negative 2y, which equals the 2 on the left-hand side. And then I can divide through both sides of the equation by negative 2. So my answer for y is negative 1. So this ends up being negative 1. And once I know that y equals negative 1, that's one of my two solutions, then I can go back and plug it in up here in this equation we started off with, and now I know x equals negative 1, because it's equal to y. So that's the values of x and y in that system of two equations and two unknowns. I hope this helps.